Excellent. Well, thank you for joining us today here after lunch. My name is Sam Grove. I look after software products, marketing, and ecosystem at MIPS, and I'm joined with...
My name is Knute Lingaard. I am a Director of Performance Architecture at MIPS.
Excellent. And we're going to talk you through some simulation technologies that we use to automate and do design space exploration and package this up as a tool that we feel solves the hardware-software co-design problem that many companies in our industry face. So if we look at all the complicated steps that are involved in designing soft IP, integrating lots of soft IPs, and putting it into an emulation system, validating that everything works as it should, and then, oh yeah, you gotta put some software in this thing to make it work. One of the things that we've been exploring over the years is how do we reduce the friction that it takes to do all that? And not only friction for us as a company doing soft IP, but also engage more deeply with customers who have very specific workloads that they care about that might not match directly to dry stones and core marks and Geekbenches and spec-ins and so on. So we're looking to completely shift when software gets involved in this development methodology. And why, right? Because at the end of the day, we don't want a sad robot, right? You built this really awesome thing, physical AI is so cool, but if you gotta plug it into a wall because you blew your power budget or your software didn't run that well, like you kinda missed the point. So everything we're doing here is to accelerate what it actually takes and means to build the right product the first time with intention from that spec phase of putting something together before you tape out and get to production.
And that's essentially where my team comes in. So the idea is what Sam was talking about. You have your software, you want to be able to run it on microarchitecture, you want to see where is it, how well is it performing, and so forth. One of the very first steps you do is typically use a functional processor model, an ISS, or some kind of virtual platform that does everything functionally for you. What's nice about that is you can do immediate software porting, you can do code generation testing, you can actually do some functional debug testing, you can improve essentially upon your application as you're building it for the specific target. So we have specific componentry that's associated with it and connected to it. The functional model can also give you some general profiling information if you do with timing annotations like loosely timed models and so forth. Architectural trace, but you can also do what's more specific, an architectural trace capture. Whereas essentially the functional model is executing your code, it can capture the instruction flow of your workload. In that mode, you can give it to essentially the next level of analysis, which is your architectural performance model. These are more specifically timing cycle approximate models. They're not ever cycle accurate models, only RTL is cycle accurate. So these models get extremely close to essentially the actual RTL. They're high level models, virtual platforms. Ours are written in C++. These models can give you all kinds of identification of how that workload and the customer workload runs. It can tell you, for example, how you can potentially change your pipeline topology. What can we do to actually do more analysis on your characterization? So we can tell you, for example, running your workload, how well it would perform on a MIPS-based processor design. With that, you can do look at early performance target insights, what you want your software to achieve as far as its performance targets, and the performance model can provide that data for you. We can do design choice trade-offs, microarchitectural changes potentially that you want to discuss with us to figure out how you want to make changes to make it work best for your microarchitecture, or at least give us an insight of what your application is doing. You can understand latency impacts where it comes with instruction latencies, how do those impacts work, memory, what instructions should you use, how far memory should be, what kind of memory you need, that kind of thing. All this data would be essentially provided to you in a pipeline deep introspection through what's called a profile data. So our performance models are capable of producing a performance trace or a profile, and right now we're using a format called HDF5. That performance data is actually fed to MIPS Atlas Explorer, which is what, if you attended Mark Fronson's speech earlier today, that's what he was talking about. This Atlas Explorer, and Sam will go into a little bit more details, but through that performance data, you can now see like summary information. What did my application generally do? You can look at timeline views. You can look at attributes of your program and how each one of those instructions as it flowed through essentially the representation of the MIPS architecture, how it actually interacted with the MIPS architecture and how it goes back to your original binary down to the source code. And it shows you exactly, this is where your loads, for example, are taking the most amount of time. You can do comparison of reports if you make tweaks to your software. You can look for custom data filters, and you can also, for example, share reports with your colleagues, say, hey, there's a way you can actually improve. Here's some problems that essentially MIPS tools found.
That's really important, right? So when you're looking at the data, right, as this comes out, so you have a functional model, you wrote some code, you have your architectural model, you now have a whole bunch of data that was produced about how it actually progressed through the pipeline. Well, like, what do you do with it? Right? Now that you have all that, and so that's what the solution entirely encompasses. And so, you might not be an expert in a particular area, so when you create these reports, you might want to share them. Or, you've identified some sort of a set of patterns of issues you've come across, create a custom filter. Now you can, we talked about automating these workloads, you have that custom filter, you run things through it, you flag pass or fail very quickly based on the output. So one of the things that we were talking about is the reproducibility when you're using a system like this. You can run things through again and again and get predictable results. And so that then means you can change two different aspects of the way you work. So one is you could have a fixed model of what you're running against, and now you can go tune and tweak your software. Do your typical flag mining, look at different options in the compiler, and during your compiler development, understand how that generation sequence of code is actually impacting the final result. But you can also flip it around the other way, where you can fix that workload and run it through and tweak the knobs on the architectural model to understand if increasing something here or decreasing something there actually will make this run better. And again, you put all this stuff into loops and you're automating your design exploration process, both from software optimization's perspective, but also from the actual design, the microarchitecture that you're developing. And it doesn't stop there, right? So a lot of these technologies, these boundaries, this is architected to be a composable system, right? So based off of that functional model, you can still connect other peripherals and other sensors. And maybe you want to connect into a physics or a linear algebra or a numerics-based simulator because you have a battery, or you have a motor, or you have something else that's modeled. All these pieces interact and connect through standard interfaces. And at the end of the day, that's your digital twin, right? So if MIPS is a small part of it with a processor model and the microarchitectural performance model, that's great. But all of that still remains compatible with the rest of your system as you build out and scale to a virtual SoC or a virtual ECU or any other virtual representation of your end device. And one of the things that's really exciting as well is it doesn't have to end there, right? So once you do get to production silicon, you're in the market, you're shipping your products. Now, how do we actually take advantage of end-trace data that comes off of these devices and actually fit that back into the tool as well? And the whole time, you're no longer stuck in one world or the other. If you think about Atlas Explorer as this horizontal solution for visualizing how software runs on hardware, you can take your path on one side, which is through simulation technology that only gets better over time, or you can take your path on production silicon, and you end up at the same spot. Now, what you see might be slightly different because you're going to get more insights out of the simulator than you're going to get off the silicon. But the point is, you are in a singular environment, and the two pieces come and work together. So if we look at these technologies and how they've all fit together, we can kind of redraw the ideal development flow or our diagram. And what this actually means is your software development has now shifted entirely to the left to match your system requirements and specifications. And what this means is if your architecture and your hardware and software teams come together to draft and write how they think the system's gonna work, you can go off into two separate directions, right? The software team goes off and builds the functional models and the microarchitectural models. The hardware team goes off and starts the RTL implementation and design. Now, throughout the development lifecycle, you come back together at these different points to synchronize. Do we understand? Did we diverge? Are we meeting expectations, missing expectations? And correlate this design back to each other, right? And each time you get further down and you validate and you're looking at your area, this whole system is put into place. And now when you're done and you're at chip fabrication, the amazing thing is like your whole software stack and application can be done. And now all you have to worry about is your long-term support and maintenance and what you're gonna go do in production, right? You're gonna be doing some sort of firmware updates and a customer's gonna come and knock on the door and say, I wish I had this new feature, right? Software is no longer backlogged at the end of the hardware development lifecycle. It's now part of it. It's done in conjunction. And by doing this, you get the software lens, the software visibility into the hardware world, and you get this point of collaboration that we think makes an ideal development flow. So just to give a couple pictures of what this all looks like, right? So on one hand, the database is produced of performance data, and we can draw really awesome graphs and charts, right? Typical flame charts, call graphs, things like that. And you have all the metadata associated with this. Is it in M mode? Is it in S mode? Is it in U mode? You in the kernel? You in the user space? All those details. And we mentioned that all of this data is microarchitecturally specific to the processor that you're modeling. So you can even look at, for example, our i8500s and the multi-heart, multi-threaded architecture, and you can actually see which instructions are making it through which of the pipelines, right? Which of the hardware threads are running which parts of the code. And all of this synchronizes back to the source code, right? So when you use the system, all you need at minimum to make this work is the trace to feed it through. But if you keep your source code and you want to annotate back to where in the code all of these points of pressure have existed, you can. And that's all those little markers on the bottom. Those are hazards and other choke points or other microarchitectural events that happened. And you can take that and line it directly up to what part of the code path caused that issue and start to look at dependencies before and after in terms of what's actually causing these challenges in the system. So what we like to say is, we're trying to reinvent the customer journey, right? We've been at this for quite a while, and we have a fundamental belief that the earlier you have insights into what the design should be, the smarter your design is going to end up being, okay? And what this means is not only are we shifting left software development, it's actually a collaboration and a co-design between hardware teams and software teams. So yes, you can port and you can debug and you can get all the concerns that you might have out of the way. What does it take to move from vendor A to vendor B, or from ISA A to RISC-V or anything else like that? That's all well taken care of. But beyond getting to just that point and understanding that your software works and building up your confidence, you're also able to start your optimization exercises to get well ahead of your product's availability in the market, right? And it doesn't stop there. Digital twin integration for companies that are really forward-looking and doing lots of simulation-based development plugs right in. So what we like to say is this will take you from design through production, right, in the product lifecycle. So we'll close up here and just talk about MIPS efforts at RISC-V International. So I'm joined here with Knute. You want to talk a bit about the performance modeling?
So I'm the co-chair of the performance modeling SIG. Specifically what we focus on is there is an open source performance simulator called Olympia. It is trace driven using the same STF traces that essentially our internal performance models that MIPS uses. Our internal performance models, for example, are rooted from essentially these open source tools. So I am currently the co-chair. Arup Chakraborty is the chair of that specific SIG. And we very much keep the SIG is actually making very good progress and a lot of exciting new ideas and directions we want to go. It's also a performance model we were intending to expand, and we're talking to other vendors and so forth and other companies that also are very much engaged in it. Yep.
And then I think I see Robert. Are you there? You want to raise your hand? So Robert works for MIPS as well. He's the chair of the ntrace technical group. And so that's where you can see our interest in bringing the ntrace into the system as well for silicon at the end. Fits quite nicely. And we look to engage more. So if you find anything we talked about here interesting, or you're aware of other groups at RVI that we should talk to or potentially engage with for simulation technologies or for other related technologies, come join us because we're looking to get more engaged. Thank you all for your time.
Thank you.